Ladies and gentlemen, it's my pleasure to introduce to you Professor Sergeyev, Yaroslav, who is a distinguished professor at l'Università della Calabria, Cosenza, professore per chiara fama in Italia, and he is professor at Russian University. He's a famous scientist, not only since he is working in the field of cooperation between Italy and Russia. By looking at his CV, you can find a lot of papers dealing with a new idea about a new computer able to deal on infinite and infinitesimal numbers. You can look at the title of the conference. Professor Sergeyev had a very impressive long list of awards and distinctions, papers on international journals. He was invited to give plenary lectures and tutorials, and he disseminated his ideas on media, even in Italian newspapers and magazines. You can find interview and a lot of articles. So I invite Professor Sergeyev to give this talk about the infinity computer and numerical computations with infinite and infinitesimal numbers. The talk will be divided into two parts of about 45 minutes each. Thank you, Professor.
Professor Longo, thank you very much for introducing. This is the first time I stand up, because then I will sit and will not move due to the camera. So for me it is really a pleasure to be here. This is my first time in Cisterna di Latina and in Centro Tullio Levi Civita, because as you will see, my research is directly related to his research, and so there is really a big emotion for me to be here. I hope that you will enjoy this new way of thinking and this new way of doing computations. So now let me start. So our talk will be divided in two parts. First we make some preliminary observations and reflections, and we'll introduce this new numeral system, and then in the second part we will see a number of applications in various fields. So you know that infinity is not easy thing to think about. For example, these words of Jorge Luis Borges reflects very well what people usually think about infinity. And I will present a new point of view, which is based on a series of patents in Europe, Russian Federation and United States that show how it is possible to construct a new kind of a computer working numerically with infinities and infinitesimals. And I will explain with which kind of infinities and infinitesimal it is possible to work. My work is based on this book. This is a book written in a popular manner, and a dozen of papers in international journals. Recently it has been there has been published a special issue from the journal Applied Mathematics and Computation dedicated to this kind of stuff, and there exists also an internet site from where it is possible to download many papers written by our group. So, fortunately, this work has been noticed by many organizations, and I was awarded several awards and distinctions, and now I start I go to the meet and I start to present. So first of all, of course, it is necessary to remember that we when we start to speak about infinity and infinitesimals, then this topic is very, very old. It is necessary to remind, first of all, Aristotle, who has subdivided the notions of potential and actual infinity. Then Leibniz has introduced infinitesimals. Then, of course, Tullio Levi-Civita, who has introduced, and here it's important for our talk, fields, Levi-Civita field, and this is a non-Archimedean ordered field containing this kind of numbers. So we have a sum which goes on all rational numbers, and epsilon here is a positive infinitesimal, a generic one, and a is a real number. So simple examples. This one, this one, this one are all members, inhabitants of the field of Levi-Civita. It is necessary to say that this series should be considered formally, so without studying problems of convergence or divergence. There exists a huge field called exactly in this way formal series, and later I will show you where there is a link from things that I do and things that Levi-Civita did. I should say that now in automatic differentiation this kind of stuff, Levi-Civita fields, are used strongly by people working in States, also in Canada. Now, infinitesimals have been reintroduced in the practice of computation by Abraham Robinson, who has introduced in 60s his non-standard analysis. You all know perfectly that infinitesimals of Leibniz have not been accepted by mathematical world at that time, and they have been substituted by the concept of a limit introduced by D'Alembert and Cauchy, and so all of us, we have studied this kind of analysis. And Robinson has shown that original analysis of Leibniz can be rewritten in a modern fashion with infinitesimals, and this was a very interesting result. Unfortunately, or fortunately, it depends on the points of view, it has been proved that all kind of stuff that can be proved in traditional analysis can be proved also in non-standard analysis, and vice versa. So from one point of view, this is a great, let's say, rehabilitation of analysis of Leibniz. From the other point of view, this result can be viewed as a certain limitation of the force of non-standard analysis, because then it becomes the question, let me say, of interpretation. Which kind of interpretation you prefer? That one that uses limits and the language of D'Alembert, Cauchy, Weierstrass, or this language? Okay. Now, I should add also that there were some efforts to introduce in teaching non-standard analysis, also in Italy, but up to now we can see that this teaching machine, let's say university, the courses of analysis, mainly continues to be presented using the language of traditional language of Cauchy, D'Alembert, and Weierstrass. Then, of course, if we move from infinitesimals to infinities, then we should say that the modern history starts from the famous papers of Georg Ferdinand Ludwig Philipp Cantor, who has shown in 1873 and 74 that there exist different kinds of infinity. In fact, this was a great result, and this result was accepted in different ways by different kinds of scientists. For example, Hilbert has supported strongly the set theory of Cantor, and he also written that nobody will allow us to be put out of the paradise of Cantor. On the other hand, Poincaré was against Cantor's set theory, and he He called this the illnesses of a childhood of mathematics, fog on the fog, and so on. I should say that this probably was the continuation of the dispute, because all of us know that Hilbert has presented his famous 23 Hilbert problems in 1900 in Paris, in the second mathematical congress, and these problems have shown the road of the development of the mathematics in many sense. But less people know that this was the second congress. But before the second congress, obviously, there was the first congress. And in the first congress, Poincaré was the main speaker, and he was presenting mathematics from another point of view, not as an abstract building, let's say, but as a natural science, and he spoke about strong connections with physics, with also engineering, and so on. So these 2 points of view have been presented by probably the most famous mathematicians of that time. And in the 20th century, the point of view of Hilbert was significantly, had significantly more strong positions than that one of Poincaré, probably because the influence of Hilbert continued many decades after the death of Poincaré. And my talk will support the point of view of Poincaré. So I will try to show you where in and how we can look at mathematics as natural science. So this is an introduction, and now I remind you that after appearing of the set theory, immediately there was a number of paradoxes. A number of paradoxes has been discovered. Of course, these paradoxes we should say in this way, because these results are theories in the Cantor approach, and I will show you for students who are here one of the simplest ones. So imagine that we have a grand hotel which has an infinite number of rooms, and all of them, there are guests in all of them. Then a new guest arrives at the hotel, and it is necessary to put the guest inside. So what is possible to do? It is necessary to move the guest occupying room 1 to room 2, the guest occupying room 2 to room 3, and so on. So after this procedure, we'll see that the first room becomes empty, and we can put the new guest inside. So if we look at this point from the point of view of finite mathematics, then we see that there is something which usually there is a situation which usually we use when we try to prove something using the method of absurdum, because we have supposed one thing, then we made a number of steps, correct steps, then we see the opposite. So there is something that doesn't work. But this is in the finite world, and traditional mathematics says us that in the infinite world it is necessary to behave ourselves in a different way, and this is one of the peculiarities of the infinite world. I will show you another situation where we show that when we are in front of infinity or infinitesimals, we behave ourselves in a different way. I do not discuss here, is this example correct, paradox correct or not correct. For me, it is important that we behave ourselves when we face infinities and infinitesimals in a different way. Let us see this simple example. Suppose that we have this x, then we multiply both parts by 2, then we add 1 on the left and on the right. Then what is this? This is x. We substitute, simplify, and we obtain this result. You see, this is a very strange result. We have an infinite sum of positive integers, and the result is negative. So of course we can say that, oh, but this is a divergent series. We should behave ourselves in a different way in front of such an object. And this is exactly what I would like to emphasize, that when we work with infinities, traditionally we behave ourselves in a different way. And our goal will be to develop such a kind of calculus and such a kind of a computer device which would allow us to work in the same way with all numbers. Let me say that when we work with 10, 12, 100 and so on, with all these kind of numbers, we behave ourselves in the same way, the same operations. We will try to do this with infinities and infinitesimals. Now, all of us know that computers work only with finite numbers, because when we start to face infinities, we have difficulties. We have undeterminate forms. We should understand that we do not know how to store infinite numbers in the finite computer memory, and this is not clear how to do. And we would like to solve these problems and to construct such a computer. In order to proceed, I need to remind you this distinction between numerals and numbers. So, a numeral is a symbol or a group of symbols that represent a number. The difference between numbers and numerals is the same as the difference between words and things they refer to. So, a number is a concept that a numeral expresses. For example, these symbols, and these symbols are different numerals, but they represent all the same number. The rules used to write down numerals together with algorithms for executing arithmetical operations form a numeral system. So, some numeral system can be more suitable and more comfortable and more powerful than another ones. And I would like to show that when we work with finite numbers, then we use the same numerals for all purposes. We use the finite numbers. When we deal with infinities, this is not the case. For example, this numeral is used in standard analysis, this for working with ordinals, this for dealing with cardinalities. Then there exist non-standard numbers using a generic, for example, infinitesimal h. And we would like to develop numerals that we will use in all the occasions when we work with infinities and infinitesimals and finite numbers. Now, remind that different numeral systems can express different set of numbers, and they can be more or less suitable for executing arithmetical operations. For example, we think usually that with positional system we can express any number, but this is not the case. For example, irrational numbers cannot be expressed in the positional system by a finite number of symbols, because we are not able to write down an infinite number of digits. So what people do, they introduce special numerals indicating this precise quantity. But the difference is also in the fact that, for example, even if we are in the finite world, there are limitations. For example, if we consider 10 power 100 digits, then nobody, even with the modern computers, is able to write down such a long number, because this number, 10 power 100, is more than the number of particles in the universe, as physicists think about. So there are practical limitations, and in order to compute, we need to write down or to represent numbers, so to have numerals that can be written down or erased. Then there exist numeral systems that are weaker than the positional one. For example, the Roman numeral system is not able to express zero and negative numbers, and such an expression is an indeterminate form. Look, numeral systems in the history of humanity have been introduced very, very rarely. And so people living in that precise moment of time usually think that with this numeral system we can express any number. And this is not the case. I have already given you an example with positional systems, but also here. What does it mean that Romans did not know zero? This means that they were not able to write down any theorem, let's say, including -3, -4, which were distinguished because they did not have any information about presence of these numbers. So numeral systems limit our possibilities to write down and to say theorems, phrases, and so on. For example, Wittgenstein, there is this famous phrase of Wittgenstein that I can think about things for which I have words. Otherwise, if I have no words, I cannot think about. But there exist even weaker numeral systems. For example, let us remind a primitive Amazon tribe of Piraha. You can read about in Science, for example, in the number of October 2004. They use only numerals, one stroke and two strokes. So through these numerals they are able to see only numbers 1 and 2. And for them, all numbers that are larger than 2 are just many. So 1 plus 2 gives the same result as 2 plus 2. Many. Of course this happens not because 1 plus 2 is equal to 2 plus 2, but due to the weakness of these primitive numeral systems. So Piraha are not able to say a word about 5, 6, 7 because they do not know these concepts. And they live nowadays in Amazonia. So I speak about them due to two reasons. The first, I would like to show you that numerals are instruments of mathematicians. Physicists have the object of the study, an instrument, and then there is a researcher. In this triad, physicists know very well that the instrument bounds the possibility to observe the object. A physicist cannot touch the object directly because there is always an instrument. And quantum physics tells us that the instrument can also interfere with the object. Now when we speak, when we understand well these distinctions between numbers and numerals, we see that numbers is an object of the study and we are not able to touch the number directly. We always need an instrument, numeral systems, to express them. I would like to say that Archimedes, for example, understood very well these kind of things. When he has written his famous text Sand Reckoner, where he tried to calculate the number of the sand on the beach and other huge numbers, he was forced to invent his own numerals to express huge numbers. Now, let us return to Piraha. The arithmetic of Piraha is very interesting because it has also this peculiarity. Look, for them, many plus 1 is equal to many, and many plus 2 is also equal to many. Now, let us substitute many with our usual sign of infinity. So what do we see? We see that we behave ourselves with infinite numbers, or with infinity, in the same way, like Piraha behave themselves with respect to finite numbers, 4, 5, 6, and so on. So, probably our difficulty in working with infinity is not connected to the nature of infinity, but is the result of the inadequate numeral systems used to express infinite numbers. So, after this observation, we move our attention from the object infinity to the instrument numeral system. So the difficulty which we have is not related to the object, but is related to the instrument. As we can see, introducing numerals to express in 3, 4, 5 and so on, we can distinguish better finite numbers. Let us try to introduce also new numerals to express infinity. I would like to say that in Piraha, the answer many is not wrong. It is correct, but this answer has a low accuracy. For example, if you ask me how many chairs there are in this room, I will answer at the first glance many, and this will be a correct answer, but with low accuracy. Now, this answer also is correct, because if we add to many chairs one more chair, we will have many chairs again. But the accuracy is low. So we would like to introduce new numerals and to see in the infinity the structure, a structure. Okay, now we would like to make practical computations, so we will not use this abstraction that we are able to write down any number of digits, for example, or execute an infinite number of iterations, because we live in the finite world and we would like to observe the result of our work. So it's clear that now I have already moved to more practical methodological positions than the traditional ones, and let us fix them better. So we postulate existence of infinite and infinitesimal objects, but accept that human beings and machines are able to execute only a finite number of operations. So a priori we accept we shall never be able to give a complete description of infinite processes and sets due to our finite capabilities. Also, it can be seen that our position is not a position of finitists who suppose that everything is finite, human beings and mathematical objects. Here we are in the middle of the tradition saying that everything is infinite, and finitism. We say that we are finite, but there exist infinite objects. So it starts to be hot. Let me take off. Okay, now, so the second postulate will follow natural sciences. When a physicist looks in his or her microscope and observes two dots, he or she does not say that the object of the observation is two dots. He or she says that with this microscope and this lens, I am able to observe the object in this way. If I put a stronger lens, then probably I see instead of the first dot 10 dots, instead of the second 15 dots, and again, these 10 and 15 dots will not be the object, but how I can observe it using this instrument. Which answer is correct? 2 dots or 10 and 15? Both, but with different accuracies depending on the instruments. So, following natural sciences, we shall not tell what are the mathematical objects we deal with. We just shall construct more powerful tools that will allow us to improve our capacities to observe and to describe properties of mathematical objects. So always in my research I will remember that there exists the object and there exists the instrument, and I will remember what is the accuracy of the instrument that I use. This is very important. Why? Because if I know a priori the accuracy of my instrument, then I will not ask questions that require answers with the accuracy that is higher than the accuracy of my instrument. And finally, we should substitute in a way this principle with this principle, because we have already seen that this situation is just a result of the numeral system which has a low accuracy. So, following ancient Greeks, we adopt the principle the part is less than the whole to all numbers, finite, infinite and infinitesimal, and to all sets and processes, finite and infinite. So, this is our point of view on infinities and infinitesimals and in mathematics in general, and we will follow it. You can see easily that this is the point of view of an applied mathematician, and this point of view follows also physicists, natural sciences. So I will move from here after working in the considering mathematics as a natural science. Now, so it is very easy to declare some things, but it is difficult, or can be difficult, to construct a way of practical computations which follow this kind of methodological platform. Now I will show you a situation and a way of counting which exists for thousands of years, but it has not been formalized so far. So suppose that this example will be very important through the whole lecture. Suppose that we are in a granary and the owner asks us to count how much grain he has inside it. Of course, nobody can count the grain seed by seed, and the problem how to count such an enormous number of objects arises. In order to overcome this difficulty, people take sacks, fill them in with seeds, and count the number of sacks. So we suppose that our sacks are very huge, and we are not able to count how many seeds there are there. Of course, we suppose that all all seeds are equal and all sex are equal. If the granary is huge and it becomes difficult to count the sex, then trucks or even big train wagons are used. At the end of counting, we obtain a result in the following form, that the granary contains, let's say, 17 train wagons, 12 trucks, 15 sex, and 54 seeds of grain. So now what happens? If I add one truck, I see that I have more, and what is the quantity that I have added. If I subtract one sec, I see that I have less, and for how much. So this is the answer with the accuracy of one grain. I would be able to say that the grain has many seeds. This is a correct answer, but with a low accuracy. This accuracy is higher. So let us think a little bit about this example. So here we worked with large quantities. They are finite, but it is impossible to count them using elementary units of measure, seeds, because the quantities expressed in these units would be too large. So people are forced to behave in front of them as the quantities are infinite. And to solve this problem, they introduced new units of measure, sex, trucks, and train wagons. Thus, it was impossible to formulate the answer in the terms of elementary units with high accuracy, but it is perfectly expressible in the newly introduced units of measure. And look, that we do not know how many seeds there are in a sack, how many sacks there are in a track, and so on. So each new unit contains a certain number ki of previous units, but this number is unknown. In spite of this fact, we are able to express the quantity with the accuracy that is significantly higher than the previous one. So it's clear now what I would like to do. I would like to move this way of reasoning from huge but finite quantities to infinite quantities. Let us do it. So let us enrich our language. I would like to say that due to postulates 1, 2, 3, we should forget about such tools as bijection, numerable sets, continuum, ordinal, cardinal numbers, and so on. Why? Because this is these tools have been developed in another methodology. Now we have another methodology, a new one, significantly more applied. I also cannot use these symbols. I should introduce new numerals, and I should develop my own tools. I would like to say immediately that what I will say now will not in contradiction with the traditional result. It is not contradiction with Cantor, with Levi-Civita, and with the non-standard analysis, with all this kind of stuff. The situation is exactly like with two lenses in the microscopes. So there is the accuracy of the traditional language, there is the accuracy of new language, and the researcher decided which lens, which language to use to work with his or her particular problem. So what will we do? We will introduce a new infinite unit of measure. It will be expressed by this numeral, 1 circled and called gross 1, in Italiano grossone. Okay, and it is introduced as the number of elements of the set of natural numbers. And it will be introduced through its properties. Analogously, when we go from natural numbers to integers, what do we say? We say, we introduce a new axiom, it defines a new object called 0 expressed by this symbol, and the rules to work with the symbols are like this and like that. We introduce this axiom, and this axiom will be added to the axioms for real numbers. Please pay attention that due to the postulate 2, which subdivides instruments and objects, our view on axiomatic systems is different with respect to the traditional one. Traditionally, an axiomatic system defines a kind of mathematical object, defines. From our new point of view, we say that axiomatic systems are written by a specific language, which is an instrument. this language has its accuracy. So it does not define a mathematical objects, but it defines some symbols and formal rules working with these symbols, which reflect some, not all, properties of the object. So we have our instrument. This instrument has its accuracy, and when we use this instrument to describe a mathematical object, then what happens is that we can say, using this language about the object, only things that this language allows us to say. Okay, now, so we have introduced this new element. And this is not new. Such a kind of stuff is not new in mathematics. There is things very similar. For example, in the theory of probability, in axiomatics of Kolmogorov, we can describe events in two different ways. Or like, as union of elementary events, or as a sample space from which we have taken its parts or have subtracted some elementary events. So we will do something like this, but not precisely, not exactly. Now let us see the properties of gross one. First property, we would like to introduce an infinite unit of measure, and we say that any finite natural number n is less than gross one. Then gross one is a number, so multiplied it by 0, it gives 0. The difference gives 0, and so on. I could even not say about this explicitly, because if this is a number, it should be like this. I would like just to show you that in our analysis there will not be indeterminate forms like infinity minus infinity, infinite divided infinity, and so on, because we have introduced a new object. Analogously, when we have introduced 0, then there is no indeterminate form of the type 3 minus 5, because we have negative numbers and we can work with all of them. So the second property, the third property of gross one is the most interesting. So we have introduced gross one as the number of elements of the set of natural numbers. Think about the set of natural numbers as about our sec, and gross one the number of the seeds in the sec. So we postulate that our sec can be subdivided into equal parts, this and this. Look, I cannot count this 1, 2, 3, and 4. Why? Because due to postulate 1, I can execute only a finite number of iterations, and this is an infinite set. But here I apply in a strong form the third postulate, the part is less than the whole. I say that I do not know, let's say in this way, I do not know how many seeds there is in the sec. I do not know how many seeds there is in the half of the sec. But I do know that in the half of the sec there are 2 times less seeds than in the whole. So here we postulate that the set of natural numbers can be subdivided into equal parts. And here on 3 equal parts. So these sets will be very useful for us. What is this? This is the third part starting from 1. 1 plus 3, 4, 4 plus 3, 7, and so on. And what is this? This is the second part starting from 2. 1 plus 2, 3, 3 plus 2, 5, and so on. And in general, we suppose that the set of natural numbers can be subdivided in n equal parts. And this is the number of elements in each of them. So surprisingly, that's all, and now we can start to measure infinite sets. For example, how many elements there are in this set? This is easy, because this is the 5th part starting from 2. 2 plus 5, 7, 7 plus 5, 12, so it has gross 1 divided 5 elements. How many elements there are in this set? Also easy. This is the 10th part starting from 3. 3 plus 10, 13, 13 plus 10, 23. So it has gross 1 divided 10 elements. We can also measure more complex sets. For example, how many elements there are here? This is the answer. Because the intersection of these 2 is empty, then 2 is here, 3 is here. So we have added 2 new elements, and we have written this here. So we are able to measure different infinite sets, also of a more complex structure. And we can also write down new numerals and to interpret them. For example, what is this? This is the number of seeds in a sack from which we have taken 2 any seeds. Or this is the number of elements in the set of natural numbers from which we have subtracted any 2 numbers. What is this? This is the number of seeds in 6 tracks minus 2 sacks plus 3 seeds. In order to understand what is from the point of view of the set theory, it is necessary to understand what is this. And this is easy. This is the number of elements in the set of couples of natural numbers. So here we have 2 positions. Each of them can be filled in with gross 1 possibilities. And here we can write down some of these couples. This is the first, up to gross 1. In this column up to gross 1, so gross 1 multiplied gross 1 square. And so on and so on and so on. Now, so we have introduced gross 1 as the number of elements of the set of natural numbers. So gross 1 is the last natural number, analogously like 2 is the number of elements of the set 1, 2, and this is the last number in the set 1, 2. And this means that all these numerals represent infinite natural numbers. If you have a difficulty to accept existence of infinite natural numbers, this is because traditional numeral system did not allow us to see these numbers. Remind that Piraha are not able to see 3, 4, and 5 by these numbers are there. Then let us make an experiment. Let us take a numeral system of Piraha, so we are able to see only 1 and 2, and add a new numeral, gross 1, to this numeral system. What do we see? In the set of natural numbers, we are able to see only these ones. So 1, 2, these infinite numbers and these infinite numbers. And what are these dots? These dots have a very clear meaning. These dots represent numbers that are not expressible in this numeral system. So if I ask you, what is the result 1 plus 2 in this numeral system, what is the answer? I drink some water and you think. So we have this instrument, this numeral system, and would like to add 1 plus 2. What is the answer? So the answer is no. 1 plus 2 is equal to 3. Okay? But here in this numeral system we have no this numeral, we have no 3. So the correct answer is this numeral system is too weak to express the answer. It is necessary to introduce a stronger numeral system which has a numeral 3 to express it. So look, this is very, very important from the methodological point of view, because this means that in our language we can have questions that can be formulated by the answer cannot be expressed in this numeral system. We are not able to say 1 plus 2 is equal to many, because now we understand that many is a low accuracy result. So 1 plus 2 cannot be calculated, because we have no numerals in this weak numeral system to represent the result. Okay, now any numeral system has its limitations, and there are questions that cannot be answered. For example, let us consider the set of extended natural numbers. So from 1 to gross 1 we have the set of natural numbers, and then there are gross 1 plus 1 and so on. How many elements there are here in this set? The answer is analogous. We are not able to answer because this numeral system with gross 1 is too weak. It is necessary to introduce gross 2 or gross 3 in a reasonable way. Okay, now let us see what we can say if we speak about sequences. Now I will try to show you what can we say with respect to some traditional mathematical object. A sequence, an infinite sequence, is a function having as the domain the set of natural numbers. But we know that the set of natural numbers has gross 1 elements. So we will call these sequences complete. What does it mean? This means that if we start from 1 and we'll try to take sequentially 1, 2, 3, and 4, we are able to arrive only here. If we start from 2, we are able to arrive here. From 3, we are able to arrive here. Now we are able to see not only initial elements of the sequences, but also the finite one. And we are able to distinguish different infinite sequences, one from another. And what is a subsequence? A subsequence is a sequence from which we have subtracted some elements. So they can be sequences that have less than gross 1 elements. For example, these 3 sequences, look, they have the same general element, but they are different. They have different length. This has gross 1 elements, this has this number of elements, and this has this number of elements. Now we can, you know, in a finite sequence, we are able to see the initial element and the final element. Now the same can be done also in infinity. We can see the initial element and the finite element. Now, I remind you that I have promised to show how it is possible to construct a computer. Let me show how it is possible to represent infinite and infinitesimal numbers in its memory, in the memory of the computer. We will use this record. So this is a positional system with the infinite radix, infinite base, gross 1. C are called gross digits, and they are traditional numerals representing finite numbers. Then P are gross powers. They can be finite, infinite, and infinitesimal. They are ordered. And there is a special power P0 equal to 0. Let us consider an example. Suppose that we have no positive powers and we have no negative powers. So everything is reduced to this. I remind you that gross 1 power 0 is equal to 1. So everything is reduced to this, where C is a usual finite numeral. So finite numbers represented by this way is just a particular case of this general record. We can represent numbers having different infinite parts, different infinitesimal parts, and to work with all of them in the computer. I show you now the first simple application. This is a calculator allowing to execute 4 arithmetical operations with infinitesimal and finite numbers. So the first example will be very easy. Let us take this infinite number, infinite because it has a finite positive gross power, 35.9, and the second argument will be also infinite with this power. So let us sum up. So as in any positional systems, first we have higher powers than lower powers. Look, usually in the traditional positional systems, we do not write down explicitly the radix, the base of the positional system. Because if we have empty positions, then we put 0, 0, 0, 0, 0. Here we cannot put explicitly 0 because they can be infinitely many. So we write down explicitly gross 1. Subtraction. The second operand goes with the sign minus. You remember that it was very useful to have negative digits. Gross 1 minus 2 seeds. It is possible to write down with the finite number of symbols an infinite quantity. Multiplication. We sum up the powers and multiply the digits. And division. We subtract the digits and divide we subtract the powers and divide the digits. Let us now add a finite part, so it has 0. It has 0 as power, and then let us add an infinitesimal part. So it should have a negative finite gross power. Now, sum up. So you see the power point pi 5.7 is between 35.9 and 0. If we make subtraction, it goes with the negative sign. Multiplication, we sum up the powers and multiply the digits. And division is subtraction of powers and division of digits. So we are able to work with all of them. So now you can see that if you remind now Levi-Civita the field, you can see that this object is very similar to Levi-Civita numbers. It is not the same because Levi-Civita worked with a generic infinitesimal. Then he worked with series. This is not a series. This is a number with a well-defined member quantity of items in the sum. Then P can be itself a number of this kind, and so on and so on. So here we have a concrete representative written in a new numeral system. But 100 years ago, Levi-Civita has seen this direction. He has not divided object from the instrument, one of the most important things here in what I am saying. But the objects are very interesting. Now, infinitesimals. So, the simplest infinitesimal is this one. This is opposite with respect to the multiplication to gross 1, and all infinitesimals are different, are not equal to 0. This is, for example, positive because we divided one positive number by another positive number. Now, let me show you some examples where in practical computations this computer can be useful. The first example is very easy. Suppose that we have a function j of x, and it is represented by a computer procedure calculating f of x, but we need its derivative. So people try to use, for example, this kind of approximation. So we would like to have a better approximation, and we try to decrease h, but unfortunately, since the number of digits in Mantis is limited, after a small h, these numbers in numerator will be equal and we lose the accuracy. Now, what the infinity computer allows to do? I show you an example. Suppose that this is the function and this is the procedure, but for me, for the user, I do not know how this procedure works. It just represented in the infinity computer. And I would like to know not only the value, but also the first, second, and third derivative in this point. Instead of using this formula, which are dangerous because we lose the accuracy, we do this. We evaluate the function in the point 5 plus gross 1 minus 1. Look, first of all, I do not know how this procedure works. I just I just evaluate. Then computer executes the procedure. And it does this not symbolically, but numerically. Okay? So, it will multiply these three numbers, and this will be the answer. Now look what happens. 125 is the exact, not approximative, value of the function. This gives us the first derivative, this the second, and this the third. So we have exact, the word exact means with the accuracy of the procedure, we have written the result, calculated in numerically and not symbolically, because there exists symbolic software codes which take your procedure, then rewrite it in symbols, then rewrite back, and so on. Here we work numerically, and I would like to show that we have constructed a general purpose computer, and this is just an example, not an ad hoc software. The second example, we have this linear system, this is the answer, and if we want to calculate, to solve it by the method of Gauss, we should to change the lines in our system, because here there is 0 and it is necessary to divide by 0, but this is not possible. So we should to execute the pivoting procedure. But traditionally, now with the infinity computer, what can we do? We can put instead of 0 gross 1 minus 1. What happens? We solve this perturbed system and we obtain this result. So this is the solution of the perturbed system, and it consists of two parts. The finite one, that is the solution of the exact system, and the perturbation, infinitesimal one. In the computer, the finite part is separated from all the infinitesimals. So we have, let us look at this example in a wider perspective. We have a program, we are not able to calculate it at a certain point. Now we perturb it. Traditionally, if we have, for example, perturbation equal to 10 power minus 7, in the obtained result, we do not see where there is the impact of the perturbation and where of the original system. Now, we are able to subdivide them, because this is the exact answer and this is the perturbation. We are able to see them exactly. And this is a huge advantage, because traditionally people use different perturbations trying to understand where is the limit of the system. Here we can calculate it directly. Another example from the optimization. Suppose that we have this is the result from this paper of Renato De Leone and Sonia De Cosmis. Suppose that we have this problem with subject to this constraint, then the Karosh-Kuntaken point is this, and pi is this. So when we work with penalty functions, we do not know how to choose the penalty coefficient, because if it is too small, then we can lose the solution. If it is too huge, then the methods usually work not so well. Now we can take this infinite penalty coefficient, and for sure it will be okay, because it will be larger by definition than any finite number. Then we write down the first order optimality condition, and we have this system, and if we solve it, we obtain the solution from where we can separate the exact solution immediately. And also we can obtain pi in the same way. So here this is a very interesting result, because here we are able to substitute an iterative method, optimization method, by the exact solution that usually can be obtained only analytically. Because this can be done if we have a paper and a pen and we can calculate. Here we can do it automatically. So I think that this is a good point to stop this first part, and then we will return after a break.
The derivatives in one point. In your example, you used a polynomial function, x power 3. Does your method work even for not polynomial functions?
So the situation is the following: that computer can execute 4 arithmetical operations with data. So when we think about, for example, sine or cosine, okay, we think that this is an elementary function, but this is not the case. So we have a procedure which calculates it in a way. Then my computer will execute this procedure and will give you a result which will be exact with the accuracy of how this procedure has been written. In my paper, I use an example exactly with sine. And I expand and I show you exactly. So what? Is
there any questions for the moment? No one. So we have a break and we will start.
Ok. Allora, ora vediamo un pochino di paradossi, dei problemi tradizionali, vediamo quello che possiamo fare. Allora, Grand Hotel... devo parlare in inglese, scusate. Ok, sorry. Yeah. So, let us see now some problems very well known. What can we say from the point of view of the new methodology with respect to these problems? We start with two examples we have seen before. So, here, with the Hilbert's Grand Hotel, it is not sufficient to say how that the number of the rooms in the hotel is infinite. It is necessary to say how many rooms there are in a hotel, in our hotel. And we start to move persons, supposing that we have gross 1 rooms. What happens? Starting to move persons, we arrive at the end, and we should to move the person from the room gross 1 to the room gross 1 plus 1. But we have only gross 1 rooms. So the person from the last room will go out of the hotel. Poor guy. Okay? So, the situation is exactly the same like with the traditional finite hotel. And I would like to emphasize that there is no any contradiction with the previous point of view. So is it correct that by applying this procedure we are able to put a new guest in the room number 1? Yes, this is correct. But before we were not able to see what happens in the last room, in the room number gross 1. Now we can see that the guy from the last room will go out of the hotel.
How do you define the last room? Excuse me.
Okay, we told that in our terminology we should say how many rooms there are in the hotel. Let's say gross 1 or gross 1 divided 2. Okay, so we have defined the number of the rooms. Okay, so you say in my hotel there are, as in your hotel, 20 rooms. Okay, here there are gross 1 rooms. Now, the second example. What is this x? If I tell you, please calculate me x like this, and here there is a finite number of items in this sum. This is not sufficient. It is necessary to say how many items there are in the sum. Now we have infinite numerals, so we should fix how many items there are in the sum, even when the number of items is infinite. Suppose that this is k, an infinite number, then x of k is like this. We multiply both parts by 2, add 1 and 1, and we obtain this. And now when we go to substitute, we see the last item that we were not able to see before. And we obtain this formula, which works for any k, finite or infinite. And for different k, we will be able to see, of course, different result as it happens. Because if we add something, now we are able to see that we have added. If we subtract something, now we are able to see. So the results for different k will be different. But let us speak more about series. So, for example, these two series both diverge, and traditionally this operation and this operation are not defined. Now, for us, this record, a kind of this record, is like calculate me the sum from 1 to many. So we should always say how many items there are in the sum. If here there is k items, this is the result, and this is the result. And for different values of k and n, the result will be different. For example, if k and n are equal to 5 gross 1, this is the result of the first sum, this is the second, this is the difference. If k is this and n is this, then both results are equal, and this is the difference. Look, I do not need the word series. For me, all of them are just sums with finite or infinite number of items. If k of this and then of this, then this is the result. So look, we have calculated these sums. Both of them are equal to infinite quantities, and we can easily make subtractions or any other arithmetic operations and to work with all of them. So this way of counting allows us to continue to compute in the situations where the traditional language stopped us because of indeterminate forms. And what happens when we have an alternating series? Again, we say always the same thing. How many items there are there? If the number of items is even, the result is 0. If it is odd, then the result is 1, obviously. Now, if this is the case, again, we can easily calculate the difference, because we can collect first positive, then negative items. These are two arithmetical progressions, and we can easily calculate the result. In general, now, we can move the order, change the order of adding or subtraction in the way we like, and the result will be always the same. For example, if we have this series, this one, and we know that there are gross 1 items, let us try to make these operations. First we take 2 positive, then 1 negative, 2 positive, 1 negative, and so on. But now, if we have gross 1 items, then we know that we have gross 1 divided to positive and gross y divided to negative. And this operation will not continue forever. It will stop when we have used all positive items here. And this is the remaining part. And the result will be this one. So, as in the finite case, any substitution of the items in the sum does not change the number, does not change the result. And if the series is convergent, again we say how many items there are in the sum. If k, this is the result. If k is equal to gross 1, this is the result. Look, 1 we have always as in the previous case. And this is just finite approximation, because now we are able to see the infinitesimal part, and we are able to work with it. Okay, I skip that Riemann function, and let us calculate now the number of, I become closer and closer to the result of Cantor. How many numerals there are in certain sets. For example, we know that in the set of even numbers and odd, there are gross 1 divided 2 numerals. And how many elements there are in the set of integers? Very easy. 2 gross 1 plus 1, because we have gross 1 positive, gross 1 negative, and 0. You see, we can easily calculate the number of elements. Here, what happens? These are rationals, numerals of this kind. This is the quantity, because, for example, here we have 2 positions. Each of them can be filled in by gross 1 possibilities. So we have gross 1 square here, gross 1 square here, and 0. Now, so we see that independence of how we represent numbers, we can calculate how many numerals of this kind we can have. For example, here, let us represent real numbers in this kind of records, in the base or radix B. So here we have the dot, sequence of fractional digits, sequence of integer digits. We know that sequence cannot have more than gross 1 elements. So here we have 2 gross 1 positions, gross 1 integer and gross 1 fractional. And thus this is the result, because each of these positions can be filled in by B digits. Now, in this numeral system, we are able to distinguish these 2 numerals, and this is the difference. In traditional analysis, you remember that this and this would be the same, because the accuracy of traditional numeral system does not allow us to distinguish them. Now we can do this. We can also write the smallest number expressible in this numeral system and the largest number expressible in this numeral system. This means that always when we start to write down something, the numeral system we use limits our possibilities to describe the object and gives us the accuracy. We will not ask questions that require answers with a higher accuracy than the chosen one. Analogously, when a physicist put a lens in his or her microscope, in this moment he or she decides which kind of object he or she is able to observe. We do the same. Now, let us calculate the number of points at the interval 0, 1. To do this, it is necessary to decide what is the point. Usually, if we have an n-dimensional space, then a point is defined by its coordinates. Here we have only one-dimensional interval, so we just need one numeral. Numeral, because to indicate the point, we should write down its coordinate. And when we have decided which kind of numerals we use to write down coordinates, in this moment, we have decided what is the point for us, which lens we have put in our microscope. And then there is a lot of possibilities. For example, if we use this kind of numerals, then we are able to see only this number of points. So only these points, they are gross 1 over the interval 0, 1. On the positive ray, we are able to see not more than gross 1 intervals, and so the ray contains this number of points, and the whole line this number of points. We can change in different ways the numerals, but the situation is, again, I would like to say, as with the microscope. When we decided the lens in our microscope, then we have decided what can we see. When we have decided which kind of numeral system we use to represent the coordinates, we have decided what are points for us. For example, Piraha over the interval 0, 1 are able to see only the point 1.1 because they have no words in the numeral system to represent other numbers. Okay, and what about this kind of stuff? If you have these numerals, then this is the sequence of digits. The sequence cannot have more than gross 1 elements. So here we have gross 1 positions. Each of them can be filled in by b possibilities, and this is the number of points of this kind. Okay, now let us return to Cantor. Cantor has shown that there exist different infinities using his diagonal argument, and he has shown that the number of points over the interval 0, 1 is larger than the number of elements of the set of natural numbers. But he has not calculated how many. And we have done this in a constructive way. We have seen here that the number of points of this kind that Cantor has used is this one. And so, first of all, we have shown that in a constructive way that b power gross 1 for different b is always larger than gross 1. And second, we have shown that taking different b, we have different continuums, because this is the number of points in the continuum, and we have many of them. And if we have less than gross 1 position, then it will be another one. So in the constructive way, we have calculated these quantities. Now, one-to-one correspondence. So, example of Galileo Galilei, we have even numbers. We use, now I present the traditional point of view, we put under each of them natural number, there is one-to-one correspondence, and so traditionally the answer which is given that the cardinality of the set of even numbers is the same as the cardinality of the set of natural numbers. What can we say with respect to this? And this is, of course, for persons who did not know the notion of one-to-one correspondence, is very difficult to digest. What can we say with respect to this? We remember the distinction of the instrument and of the object. And the answer, first answer, what can we say? That on this picture we can see on another way that the one-to-one correspondence, this instrument is not sufficiently precise to show that these quantities are different. Okay? So if I see in my microscope one point, okay, this does not mean that all the object is I observe is one point. This means that probably with the stronger lens I will see more points there. Now let us see on this picture using our new language. First of all, we are not able to use one-to-one correspondence as an instrument because both sets are infinite and we are able to execute only a finite number of operations, and we are able to write down only a finite number of numerals. But what we do know, we know that the number of elements in the set of even numbers is equal to gross 1 divided 2. So this is the last natural even number, this is its number. This is the previous, this one, and dots represent numbers that are not expressible in the chosen numeral system. So it is correct, this part of the picture, but now we are able to see the last part of the picture that we were not able to see before. And now as you can see, there is no any paradox. Even numbers are exactly a half of the natural. Here, what can we see here? Here we can see the result of Cantor. The cardinality of the points over the interval 0, 1 is the same over the whole x. How it is proved? Let us take any x. This is a function f of x. We calculate y. Then let us take y. We calculate x. And we have one-to-one correspondence. Now, what do we say? We say that it is not the case we are able to take any x. We are able to take only those x that are expressible in the chosen numeral system, or in the numeral system the humanity knows at this as a precise moment. So the number of points here over the interval 0, 1 is defined by the numeral system, and this is the number which does not depend on any object outside the set. We have fixed our numeral system, we have certain numerals. When we started to calculate, this means that we should work with these numerals, and it is not granted that the result will be expressible with this within this numeral system. So in this picture we have three independent objects: the set of numerals here, the set of numerals here, and the function. That's all. So again, was correct things that Cantor said? Yes, because his instrument was weak and this instrument did not allow him to distinguish this object. Now the instruments are stronger and we are able to see the difference. Which answer is correct? Both, but these answers are, have different accuracies. Now, now we are able to do different things with these numerals, infinite, infinitesimals, and so on. And we do not need limits. We can have results with a high accuracy. For example, traditionally both these limits diverge, even though this expression is quite different for any finite x. Now it will be different for any x. For example, if x is equal to gross 1, then this expression gives us this result. This expression gives us this result. And we can easily to make the difference and to find this number. If limit does not exist, no problem for us, because we just say always, say us at which point at infinity you would like calculate. Fix n and you will see the result. If the limit exists and it is a finite number a, for us this is just a finite approximation, but probably now we are able to use infinitesimals in our computations and it will be useful for us. For example, this is traditional limit, this is our result, and if we consider, you asked me about non-standard analysis, this is what non-standard analysis uses. Working with a generic age, we work with concrete age. If h is this, this is the result. But h can be different, 2 gross 1 minus 1 or gross 1 minus 2 or any other h. So we pass from generic to concrete. And we can calculate also functions which can be evaluated in finite and infinitesimal points. For example, this is function, this is its derivative. If x is this, this is the result, and this is the result. If x is this, this is the result, and this is the result. And we can calculate the function in any other x expressible in this numeral system. Then we can also construct new objects. For example, this function is quadratic, but its quadratic element is infinitesimal and its linear element is infinite. This is a completely new kind of objects with which we can work, and we can also calculate it at different x, infinite, infinitesimals, or finite. Integrals, we have no now divergent integrals, because we can calculate this integral to up to this x or up to this x, and we can also calculate the integral from one point infinity to another point in infinity, and the difference of these points can be even infinitesimal, and we continue to obtain the results. And now I made, so this is what I am speaking about. We take the infinity and cut it in gross ones. When I show this picture to people from industry, they think that these are dollars or euros and so coins. You know, I just put the wrong key. Now, in traditional analysis that has been developed 300 years ago, the objects of discrete and continuous are opposite. And this was the point of view of physicists who have developed the analysis. Now, with relativity, with quants, we know that this is not the case. For example, this table, is it discrete or continuous? It depends on how we look at it, on the instrument. If we look by eye, it is continuous. By microscope, it is discrete. This function, is it continuous or discrete? Again, if these distances, are infinitesimals, then, and these infinitesimals, then it is continuous, and it is possible now to speak about levels of continuity. If we choose the unit of measure which is finite or infinite, it will be discrete. So we have a richness, and we can, as in physics, to look at this on the same object in different ways. We also can quantify delta function. Delta function is a function integral equal to 1 over a point. Okay? And at point it has an infinite value. Now, for example, we can quantify delta functions. This is one delta function, this is another one. Okay? So we choose, by choosing delta functions, the precision of the model we work with, and we can calculate it and work with it in an opportune way. Probability. So, in probability we have, for example, this situation. Suppose that there is a dot on the disk and disk is rotating. Which is the probability that the point on the disk will stop exactly in front of the arrow? What is this answer? The answer is that the probability is 0. And here we have a problem in probability, because in discrete case, probability 0 is impossible event, the impossible event. Here we should distinguish in a way what is the impossible event and what is the event which is possible, but the probability is 0. What do we say here from the new point of view? We say, sorry, but how many points are you able to distinguish on the disk? If 10, the probability will be 1/10. If gross 1, 1 over gross 1. If 2 gross 1, 1 over 2 gross 1, but always positive. It can be infinitesimal. And approximation to the finite case will be 0. Correct approximation. But now we can see more. So, as in physics, we fix the accuracy of our model and we study the situation using this accuracy. Then, we can work, as I already told, with the functions which can assume different infinite and infinitesimal values, and we can describe discontinuities. For example, here, at this point on the left, the value is gross 1 square. At point 0, gross 1 square plus an infinitesimal jump, and here another infinitesimal jump. In spite of this fact, we can write down these functions and work with all of them. We can also calculate areas of figures, because if we have chosen the accuracy of our model, then we have the granularity of our model. For example, 1 point, gross 1 minus 1, multiplied gross 1 minus 1, and we can work with this model. Fractals. This is the famous Cantor sets. We have an interval, unitary interval, then we throw out the central third part, then the central third part from each of these parts, and so on. Traditionally, it is possible to say that the series of all parts we have thrown out is equal to 1. Okay? But we can see that there are points that remain always. For example, the initial and the final point. What do we say? We say always, how many steps have you done? If you have done gross 1 steps, then you will have 2 power gross 1 intervals, and each of them will have an infinitesimal length, and the sum will be infinitesimal. So again, no contradiction with tradition. The finite approximation of this is 0, but now we can see more. And in the infinity we can distinguish different objects. They are different in the same way as this line is different from the next one. I should say that I'm very happy because MIT Technology Review has written a very nice review on one of my papers dedicated to fractals. And here there is a new kind of fractals, blinking fractals. So suppose that we have a process which, when we observed it first, it was a blue square, and then it was 4 red triangles, then each red triangle becomes 2 blue squares, so the process goes like this. So this is not fractal, because fractal is self-similarity, and the same object should be become copies of itself. Here we have a mixture of 2 fractals, this one and this one. And traditionally, it is not possible to say what will be infinity because they blink. Now we say, how many steps have you done? And I can say that it will be red or blue, how many of them, and so on and so on. So this is more or less what I would like to say. So there is this book, there is the site, I have a number of papers with me of several authors, and in June 2013 there will be a conference in La Mezza Terme where there will be a stream dedicated to these kind of things. So thank you very much for your kind attention, and I'm ready for questions.
I'm sorry, all this is rather shocking for somebody accustomed to the standard operator. But do you have an algebraic structure for your numbers? I mean, it is a field.
In your question, you mix numbers and numerals. Traditionally, people do not distinguish numbers from numerals. I do not know what numbers are. This is the object. I think numerals and work with these numerals. For example, traditionally, traditionally we speak about fields and so on, because people think that any operation can be done, but this is not the case as we have seen. When I add 1 plus 2 and I use numerals of Iraq, the answer is many, or if I am on the new positions, I am not able to express the answer because I have no numerals. So, I work with numerals. All things I say are about numerals, not about numbers. So, if I have fixed a numeral system, then of course numerals that I have are then defined. I am able to count them as I have shown. So this is not the thing. Let me use a metaphor. I have numbers. Some of them I am able to see through certain numeral systems. From Hierarchy, I can see one kind of numbers. From Roman numerals, other kind of numbers, and so on. And I do not discuss what is behind, what numbers are. I discuss only things that I can see through my numerals.
Okay. So the set of objects which are named with your numerals, is it a set of non-Archimedean field?
Again. So the question, when we speak about fields, when people speak about fields, they try to speak about numbers. I speak about numerals. And when I speak about numerals, I know how many of them I deal with. So for sure they are not the field, because numerals, 1 stroke and 2 stroke. 2 strokes are just 2. Numerals, let me show you. These numerals, okay? Usually these are considered as real numbers over the interval 0, 1. This is a field and so on and so on. But I know that this is not the field, because here only p power cross 1 numerals can be chosen of this kind. So I have fixed data from it. I do not discuss what are numbers, field, monoid, I don't know what. I see well-defined numerals and I can count how many they are. Of course they are not the field, because the operation, for example, this plus 1 is not defined because I have no numerals to express the result. As in physics, this is exactly the same. You can see what you can observe through the lens. When you can fix the lens, you are not able to see objects smaller or larger than that allowed by the field. When I have fixed my numeral system, I have fixed with which objects I am able to work. For example, the set of natural numbers. This is not even a monoid, because gross 1 plus 1 goes out of the set of natural numbers. It goes to the set of extended natural numbers. So I always remember what I am speaking about, which numerals I use, and I do not say what is the object. Physicist does not say what is behind the lens. When he looks at the microscope, he discusses what he observes. Physics does not speak about nature, it speaks about models of nature, using software. Here I try to put mathematics on the same level of the, let's say, methodology, scientific methodology, like in physics, like we have in physics now, where there is a strong distinction between objects and instruments, relativity, quarks, and so on.
Any questions?
Yeah, questions. Maybe this is a naive question here, but this is what is not clear for me. First of all, gross plus 1 let's start with your simple example of the hotel. You say when we have new income, we move the visitor from the first to the second, from the second to the third, and so on. That means we make the space in the beginning of the sequence of elements. What is the difference if we compare the situation that we put the new visitor in the end of the sequence? I mean, this is clear for me that
in the last row, you say. So we start
in the last row,
from the last row to the first one.
This is clear for me that this is somehow associated with the precision of our numbers. If our elements are the numbers, for instance. That's obvious that if you have natural numbers, we have 1, 2, 3, 4, and so on. So
and now we can count from the other side also.
No, what is important for me is that the elements are put in some order. For instance, if we consider the real numbers between 0 and 2 and 1, and we count them. We count them with certain precision. Yeah. So if we say we count the numbers which can be described using 10, only 10, the digits that can be described using 10 numbers, then we can simply count them and so on. If we say now we want to increase the number of elements, that means we want to consider the space which has the size gross plus 1. Where we put the number? I mean, this is important. In that case, we put somewhere between the numbers which we saw before, with lower precision.
Yes.
In the first example, I mean, in the hotel, we should put either in the beginning or in the end, the additional element. So for me, this theory is missing of some additional parameter which describes the precision of how.
So I try to answer, if I have understood well, to your statement. So first of all, we do not put an additional element. So my point of view is that we change the instrument, and now we are able to see the last element in the same way as Tiraka are not able to see 3, and we are able to see 3, and we think that it was 3. Okay, so we have the elements 1, 2, gross 1. Okay, traditionally people move in the hotel starting from 1. We move and we do not see them. Now we are able to see them. And the person from the gross 1 should go out of the hotel. The same would happen if we start to move from gross 1 to gross 1 minus 1, from gross 1 minus 1 to gross 1 minus 2, then the person from the first room would go out. So I do not add anything. I use another instrument which allows me to see more. That's all.
Yeah, this is clear, but you see more either in the end or in the beginning. In another case, you see more between the end
also in the middle, for example,
already visible.
Also becomes visible. Let me show you this kind of, when I can show. Here, look, we have initially only numerals of Perturb, 1 and 2. We have added gross 1. So now, these numbers become visible. Minus 1, minus 2, gross 1 divided 2, plus 1, plus 2, minus 1, minus 2. That's all. If we add 3, then it will be here gross 1 minus 3, here we will 2/3, 1/3, and so on. And they go. So instead of working only on the initial part, now we have many, let's say, islands that become visible. And when we want to calculate, we should make calculations on these islets which are visible.
I have a naive consideration of that. It seems to me that there is an analogy with perturbation methods in which you expand in series. You have different powers of the perturbation parameters, epsilon power 1, epsilon power 2, and you have gross 1 power 1, power 2, and so or minus 1, minus 2. Okay. And in this example, you are able to look at what happens close to infinity. In the traditional way, you write 1, 2, 3, dots, dots, dots. I cannot to see what happens when the number is large. But you are able to look, in some sense, it seems to be a perturbation from infinity. You put on infinite, and you are able to see what happens close to infinity, since you are able to write plus 1, minus 1, minus 2, minus 3. In some sense, this resembles me in perturbation approach what happens in a boundary line. When you have a differential equation with similarly perturbed, the coefficient of the line derivative goes to 0, we are not able to see what happens in the boundary lines. In order to understand what happens, you have to stretch. So you change your point of view, your scale, your approximation scale, and you are able to see what happens close to the boundary. Is there some, in your opinion, this is very not precise observation, but do you think to be a point to better understand if there are
I think that your interpretation is very good, because before, as we can see on this example, before using gross 1, we are able to see only one part. Now we are able to see many other parts, and by using infinitesimals, in each of these islands, we can see also infinitesimals and so on. So we can, let's say, not only microscope, but also telescope in which we have microscope inside, and we are able to see. And look, in some sense, suppose that this is point A and this is point B, which is infinity far away. Okay? If I move here traditionally, I can see that I have changed the position. But I always am infinitely far away from this point B. Now, I can see which exactly coordinate is here. And I can move here, I will see at this point what happens. If I am here and here I will see what here is happening. So for me now it's not important, am I infinitely far away or here? So this is the new way of thinking and of doing things. I tell you more. Suppose that I have this distance. Okay? This distance, is it finite, infinitesimal, or infinite? It depends on how I want to see it. Because if I see it from this distance I make here, it is, let's say, this 20 centimeters. If I am as Zeno, who makes infinitesimal steps inside, and for me the unit of measure is infinitesimal, then the distance will be infinite. If I am infinitely far away, this distance will be infinitesimal. So I can now look at the same object independent of how I wish to see it, to observe it. And this means that also in mathematics there was traditionally the final world, and then infinities and infinitesimals were just auxiliary things. Now there is no any difference. Finite, infinite, infinitesimals, all of them have the same power and the same importance. And we just decide for our concrete problem which unit of measure is better, and this is we work in it. And it is possible to speak about continuity also in infinitesimal functions or infinite functions, and continuity will be of different orders and so on. So the new language is significantly more rich, and we use, as in the final case, we use the same numerals for all the purposes.
Other questions? Another question.
I am asked about fractional geometry calculations.
Fractals, you mean fractals?
Fractals. And the problem is that when you do fractals for infinity, the processing time is very large. By this method of infinity, can you solve this problem of processing time?
I cannot understood very well the question.
The question is that can the infinity by this method solve the processing time of the processor to calculate or not?
No, you mean the physical processor?
Physical process, yeah.
So it's first of all, we live in a finite world, and we are able to execute only a finite number of computations. So what can be done with this formalism? You can observe infinitely far away certain parts of infinite fractals. This can be done, and we have a number of papers dedicated to fractals and to work with fractals, and so you can have a look and see. But of course, we should do our computations in a finite time, so we are able to execute only finite number of iterations, and so on.
If there are no other questions, I think we can thank again Professor